Hello, it's Monday, Tuesday, and we have a new DIN for this week. And the DIN this week will work a little bit differently. We are on week 2 of periodicity, that's unit 3. Unlike usually when the whole week's DIN is released at the beginning of the week, this week the DIN will be released in 2 parts. The Monday, Tuesday part, that's this part, will be released now. And later this week, when I have it ready, the Wednesday, Thursday, Friday will be released. And if you want, you can copy and paste them together or add links to link them together, or you can just treat them separately, but then you'll turn in both halves as part of the notebook check this week. Okay, so let's make our copy. And remember, and so this is just the Monday, Tuesday part. The rest will come later. We are still on periodicity, which is still all about patterns. Okay. So if I remember correctly about this pattern, this is a review from last week. Elements in period 1 have 1 shell. Elements in period 2 have 2 shells. Elements in period 3 have 3 shells. Elements in period 4 have 4 shells. Elements in period 5 have 5 shells. Elements in period 6 have 6 shells. And elements in period 7 have 7 shells. And then elements in group 1 have 1 valence electron. Elements in group 2 have 2 valence electrons. Elements in group 13, because we're skipping over that haunted D block, have 3. Elements in group 14 have 4 valence electrons. Elements in group 15 have 5 valence electrons. Elements in group 16 have 6 valence electrons. Elements in group 17 have 7 valence electrons. And elements in group 18 have full electron shells. Oh, slightly too big. Well, we can fix that. Okay. Now, this is a review. Patterns in shells and valence electrons. So which element has 2 shells and 6 valence electrons? Well, the ones that have 2 shells are the elements in period 2. That's lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. And the elements that have 6 valence electrons are here in group 16. That's oxygen, sulfur, selenium, tellurium, polonium, and livermorium. So the one that has both 2 shells and 6 valence electrons is the one that's highlighted in yellow and blue, giving it a slightly greenish tint, and that is oxygen. So now you can move around these highlights and this thing on the periodic table to answer the other questions. If we're trying to find 4 shells and 2 valence electrons, it would be calcium, for example. But use this tool now to answer practice problems 2, 3, 4, 5, 6, 7, 8, and 9. You will likely need to switch back and forth between slides 3 and 4 while you do so. Thank you for pausing. Let's move along. This looks to be another form of review. It says, we remember before that group 1 elements form +1 cations, group 2 elements form 2+ cations, group 13 elements form 3+ cations, group 14 elements could form 4+ or 4- ions, cations or anions. Group 15 elements form 3- anions. Group 16 elements form 2- anions. Group 17 elements form 1- anions. And group 18 elements do not form ions. So the directions here are to put the correct number of electrons around each atom to make it the correct charge for that group. So if this is 1 proton, it's 1 positive charge. And if it forms a +1 cation, that means there should be a total charge of +1, so we don't add any electrons to that. This is just what that ion looks like. Oh, this one's done for us over here, this helium. So we've got 2 positive protons and 2 negative electrons. And who wins, positive or negative? Well, those cancel out. And it has no charge, which means it does not form an ion. That's great. So here for lithium, we've got 3 positive protons, and we want it to form a +1 cation. So we've got 3 positive protons, and we want the positives to win by 1. So how many electrons are we going to need? Oh, we're going to need 2 electrons. We're going to need 2 electrons, so I'll grab these 2 electrons here and bring them down, and it's not going to be perfect, but we'll put the electrons around the outside as best we can. This nucleus is enlarged just so that we can read it. All right, group 2 elements form a 2+ cation. So if we have 4 positive charges in the middle, positive charges need to win by 2. How many electrons are we going to need? Well, we're going to need 2. And you can see that I'm moving around this box by using the arrow keys on my keyboard. And if you just use the arrow keys, it'll move kind of far and kind of fast. If you want to use more fine-tuned control for smaller movements, hold down the Shift key while you use the arrow keys. Okay, so keep following with that pattern, and we'll see a periodic pattern emerge. So when elements form ions, they gain or lose electrons to have full valence shells, and then their electron shells look like the nearest what? I'll give you a hint. It has something to do with group 18. But don't just write group 18 as your answer. Kind of explain more about what that means. You may also want to use the phrase electron configuration in your answer. Let's move along. Okay, now we use the periodic table on slide number 7 to answer these questions. Which element forms 1+ cations and has the same electron configuration as neon? Well, let's check. Here's the ones that form 1+ cations. And here's the electron configuration of neon. So it has a full first shell and a full second shell. And so that our answer has to be over here, sodium. So then we would write Na is sodium. Great. So you can do 11, 12, 13, 14, and 15 practice problems on your own. Pause the video now, and we'll resume in a moment. Okay, let's move on to some review of shielding and effective nuclear force. Shields exist to block things. The stronger the shield, the more something gets blocked. So face shields block the coronavirus. So people working in healthcare and some other professions have these face shields. The coronavirus itself, like the particles of the virus, which remember are matter, do through intermolecular bonding bind to water particles that are in the air, water droplets, and the face shields help prevent those droplets from getting into your eyes or nose or mouth in addition to a mask. So here we've got helmets block crash impact, so if you crash, the helmet blocks the impact from you, and full shells block the pull from the nucleus. So here we can see that hydrogen has no shield. Lithium has 1 shield from the first full shell. Sodium has 2 shields from the first full shell and the second full shell. And potassium has 3 shields for the first full shell, the second full shell, and the third full shell. And as we can see, the nucleus is a little bit dimmer every time we add one of these shells because it's shielding the positive charge from the nucleus. So elements in the same group have the same number of valence electrons. As you go from top to bottom, elements have more shielding that blocks the nucleus's pull on the valence electron because why? Pause the video now and explain why. It's another review of shielding and effective nuclear force. So lithium has blank protons pulling on electrons in the second shell. Well, there are 3 protons there. Beryllium has 4 protons pulling on electrons in the second shell, and boron has 5 protons pulling on electrons in the second shell. Elements in the same period have the same number of shells. as you go from left to right, elements have a stronger pull on their valence electrons because why? Look at the pattern and explain why. Pause the video now and explain why. Okay, so we just talked about shielding and effective nuclear charge. There's also here atomic radius, ionization energy, and electronegativity. And it looks like we have these little definition cards that we can place on each thing. So which one is how easy or hard it is to pull a valence electron off of an atom? Is that effective nuclear charge? Is that shielding? Is that atomic radius? Is that ionization energy? Or is that electronegativity? See if you can figure these 5 out before we go over it. Pause the video now and try it yourself. Okay, and here's what you should have got. So shielding is how much the pull from the protons is blocked by full inner electron shells. Effective nuclear charge is how strongly or weakly the protons in the nucleus pull on valence electrons. You can see this donkey pulling on this valence electron, trying to keep it in. Shielding and effective nuclear charge are responsible for the patterns in atomic radius, how big or small an atom is. Shielding and effective nuclear charge are also responsible for the patterns in ionization energy, or how easy or hard it is to pull a valence electron off of an atom. And shielding and effective nuclear charge is responsible for all the patterns in electronegativity, or how easy or hard it is for an atom to pull in a new electron. So we can see for atomic radius, as we go down a group, atomic radius increases. As we go across a period, atomic radius decreases. For ionization energy, as we go down a group, ionization energy decreases. And as we go across a group, ionization energy increases, so kind of the opposite of atomic radius. And for electronegativity, as we go down a group, electronegativity decreases. As we go across a period, electronegativity increases. So the pattern appears to be the same for ionization energy and electronegativity, but different for atomic radius. I wonder why. Now let's look at all 8 of these trends. 1 for shielding, 1 for effective nuclear charge, 2 for atomic radius, 2 for ionization energy, and 2 for electronegativity. That's 8. Let's look at all 8 of those patterns on one periodic table. We're going to need a bunch of arrows. And there's a bunch of arrows. So it looks like we have 3 separate word banks. 1 talking about periods, 1 talking about groups, and 1 where we just put increases or decreases on whatever the pattern is. Based on what we had on this slide and these 2 slides, I think we can figure this out ourselves. So why don't you pause the video now and go through it on your own. So then as we go down the group, shielding increases, which also means that the atomic radius increases because we get more and more shells. Because there's more shielding, that means there's going to be a larger atomic radius. So atomic radius increases as we go down. And then ionization energy, as there's more and more shielding, it's going to be easier and easier to pull off that valence electron. So ionization energy decreases. And then electronegativity, the amount of pull they have is going to be weakened by all that shielding. So electronegativity decreases as well. There we go. I believe first hour and third hour there may have been a typo on here where it said the wrong thing. I am so sorry. These are the correct answers. Okay, and now we can use this periodic table to answer these questions. So for example, we've got chlorine and bromine over here. Which one has more shielding than the other? Well, I would say bromine has more shielding than chlorine because it has more shells. Remember, more shells means more shielding, and that's also going to lead to a larger radius. We've also got rubidium and strontium, which appear to be in the same period because they're at the same level. Which one has a higher effective nuclear charge? Because it has more blank pulling from its nucleus. Well, if we go back to where we talked about that, it looks like Elements on the same period have the same number of shells. As you go from left to right, elements have a stronger pull on their valence electrons. Aha. So then I would say that strontium has a higher effective nuclear charge than rubidium because it has more protons pulling from its nucleus. And the word has appears to be missing, but oh well, such is life. I'll let you figure out the rest on your own. Pause the video now and do so. Okay, here we go. We've got metallic character. Color in the periodic table into metals, nonmetals, and metalloids. So it looks like we can grab these and move them around. And remember to hold down the shift key to get more fine-tuned movement. And the distinction here in metalloids for metals and nonmetals, it may be a little different than on previous periodic tables, but there is room for debate and argument, especially among one of these heavier elements, as to what is or is not a metalloid. Okay, and then we've got metal plus metal equals metallic bond, metal plus nonmetal is ionic bond, and metal plus nonmetal is covalent bond. Interesting. I wonder if that's going to be relevant soon. Aha! A pivot. So this is our lab for this week, Ionic and Covalent Substances Lab. So we should be able to kind of click anywhere, and move on over to pivot and log in here. So this lab has 5 parts: conductivity test, melting test, making predictions, testing predictions, and summarizing your results. You should complete all 5 sections in order to have it be completely done. Let's zoom in a little bit here. If you can't finish this all at once, make sure you scroll down to the bottom and click Save. Save. Let's start with a simple experiment. In the videos below, a scoopful of substance is mixed with pure water. Then a light bulb battery and 2 electric plates are inserted. If the light bulb glows, we say the solution conducts electricity. If the solution is not conductive, the light bulb will not glow. Okay, so here is sucrose. Let's hit play. So they're mixing the sucrose in. Sucrose is a type of sugar. Some funky jewelry dangling down. And so the experiment hasn't happened yet. They're just mixing the things. And it looks like that light bulb did not turn on. Okay, fun. Play each video and observe which solutions conduct electricity and which does not. Which solutions conduct electricity? Select all that apply. If the light bulb turns on, then the solution has high conductivity. So sucrose, did that conduct electricity? Yes or no? And before we submit answer, we need to go through all 4 and hit load and play to see what does and does not conduct electricity. Then we will submit answer and go from there. And then it gives us the chemical formulas for each substance. So we've got sucrose is C12H22O11, meaning there are 12 carbons, there are 22 hydrogens, and there are 11 oxygens. Copper 1 chloride is CuCl, meaning there is 1 copper and 1 chlorine. And iodine is I2, meaning there are 2 iodines. And potassium iodide is Ki, meaning 1 potassium and 1 iodine or iodide ion. Our goal is to try to find the pattern for which compounds conduct electricity when dissolved in water and which don't. One hint is to look for patterns in which kinds of atoms form substances that conduct when dissolved and which kinds of atoms form substances that don't conduct when dissolved. Here's a periodic table you can use. Haha, this looks familiar. Let's start by identifying the location on the periodic table for the atoms for substances that conduct when dissolved. So it looks like they did sucrose for us. Is it conductive? No. Well, that's what we saw in the video up there. It's also a nonmetal and nonmetal and nonmetal. Oh, because carbon is up here and is a nonmetal. Hydrogen is up here and is a nonmetal. And oxygen is right here and is a nonmetal. So that's nonmetal and nonmetal and nonmetal. Cool. So do the other ones on your own. Moving on. Look at the data table you made. What pattern do you notice about the metallic character of substances that do conduct electricity? You should be able to look at your completed table and answer it from there. Look at your data table that you made again. What pattern do you notice about the metallic character of substances that do not conduct electricity? Okay, moving on to part 2, melting tests. Let's explore these same 4 substances, but it's time to observe the melting point. The melting pointing point. Fun. The video below, comma, there's all sorts of typos here. Don't need the comma there. I'm going to start again. Let's explore these same 4 substances, but this time observe the melting point. The video below shows how we will measure the melting point. Watch the video and use it to answer the questions below. Okay, so here's a thermocouple. It's a type of thermometer. It measures it and displays the temperature over here on our lab quest. We have these at Roosevelt. We're going to put some drops of water on the end of it. Those drops of water are going to help this powdered substance stick to the thermocouple. And then we're going to put the Bunsen burner under it to give it some of that energy it will need to phase change to melt. And now we can see the temperature going up. And we've got this very nice camera that's zoomed right into it so we can watch it begin to melt. We can see it begin to melt and then see what the temperature is over there. So how can we tell the temperature of the substance as it's being heated by the Bunsen burner? Well, I think you can see that from the video. Now let's use this method to observe the melting points of different substances. In the videos below, we'll see a close-up of the substance being heated and the temperature in the lower left. The substance is heated with either a stream of hot air or a Bunsen burner flame. You can play the video and watch when the substance melts and read the temperature of the substance at that moment. Okay, let's try sucrose here. So there's no flame, it's just the superheated air. Oh, it looks like we're beginning to melt here. So we could have written down any of those temperatures. And then if I remember from my heating curve thing, it should reach a steady and consistent temperature as it goes through its total phase change. So it looks like it's being pretty consistent right around here. And so that was my sucrose, because it says sucrose right there. The melting temperature, I would say that one was about 193 degrees Celsius. And then we can switch and go from there. Fun, fun, fun. So then, what pattern do you notice with the conductivity? Part 3. Okay, so now we've done our conductivity test and our melting test, and we should have observed some patterns. So now we'll go through to part 3 and use the patterns to make predictions. In parts 1 and 2, you notice some patterns about what kind of substances conduct electricity when dissolved in water, and also how melting points are related. Let's test this pattern by applying it to other substances. Consider the following substances: potassium chloride, KCl, octadenocol, C18H38O, which means there's just one oxygen, and then dimethyl sulfoxide, C2H6OS, and lithium bromide, LiBr. Based on the patterns you saw in the previous sections, which of these substances do you think will conduct electricity when dissolved in water? So this has something to do with metals, nonmetals, and metalloids from before, and perhaps also with these notes from our digital interactive notebook this week. So which ones do you think will conduct electricity based on the patterns we saw up here? And then explain why. There may be more than one right answer. And when you submit your answer, it will check to see if you're right. You have 4 total guesses, but there's more than 4 ways to answer this question, because you could say that, just that one, just that one, just that one, just that one, that one and that one and this one, that one and this one, that one and that one, that one and that one, that one and that one, that one, these 3, these 4, these 3, and these 3. So more than 4 combinations to answer, and you only get 4 guesses, so make sure you really look at your stuff from before and think about it hard. and then explain your reasoning here. Also, use the patterns you saw in previous sections to predict which substances will have high melting points above 400 degrees Celsius and select all that apply here. It should be related to your answer up here. Okay, now that we've made those predictions, we are going to test those predictions. So which type of elements form ionic bonds and which type form covalent bonds? Oh, this is asking us a question directly from these notes. So use these notes to answer this question. And then we will go from there. This looks like a similar experiment for electric conductivity, where we put in the substance and stir it around so it dissolves in the water. And then there's our conductivity meter. Yay! Here's this periodic table again. And here we need to say if this is ionic or covalent bonding in each of these substances. Remember, this periodic table can help you answer that along with this stuff up here. And then here it says conductivity. It also says yes or no over there. We're going to talk a lot more about ionic and covalent bonding on Thursday, Friday. This is kind of warming us up for that. And then, then we'll see the melting points of those things and look for similar patterns. Did the predictions we made about melting points match the results we saw in the video? Explain why. Then we need to summarize our results. So we'll summarize our observations using two terms that may be new to you: ionic bonding and covalent bonding. These substances formed through ionic bonding: cuprous chloride, lithium bromide, potassium chloride, and these substances are formed through covalent bonding: sucrose, iodine, octadenocol, and dimethyl sulfoxide. Use your observations in the previous sections of this activity to answer these questions. Which of the following are properties of compounds formed by ionic bonding? Select the best 3 answers. All right. Which of the following are properties of compounds formed by covalent bonding? Select, I'd imagine, the best 3 answers. And then we're done. Just make sure you hit save at the end, otherwise it won't save. All right, that's it for today. See you later. Bye. The last thing I wanted to show you all today was this cool program called Collisions. It's a simulator where you can kind of play around with atoms in different ways and see for yourself some of these things that we've been talking about, like ionization energy, etc. So if you go into your Google Classroom, there should be a link with your class code on it. Please join the right class. If you do join the wrong class, because that complicates the grading, we will delete you and you lose all your saved progress. So make sure you are joining using the class code for your hour. So if we click into it, enter the class code, and you can click sign in with Google and just use your at mpsedu.org sign in and go from there. And then you can play these different games. And the thing I like about this is it gives you very specific directions. And it saves your progress automatically, which is nice. So this is a proton. Cool. Tap to create a nucleus and start building your own atom. So we will pull the proton into the nucleus. Great. This is an electron. This is an orbital. Tap on it and add an electron. Hey, there we go. Now we swipe left. And so we swipe up. Hey, we made a hydrogen atom. Drag it down. Hey! Easy. It gets harder from there. But play around with this, and you should be able to see things in a way that you wouldn't normally see, including struggling to pull electrons off with that ionization energy. So play around with that, and that is it for today. See you later. Bye.